Hi, my name is Ng Hin, and I'll be presenting the introduction of our MongoDB project. And the objective of this project is to design a NoSQL database model using MongoDB that focuses on the efficient storage and management of the delivery records that we have selected. This delivery record system that we selected as our real-world domain because delivery platform generate dynamic and semi-structured data such as customer detail, order information, rider assignment, and real-time delivery updates. In contrast to traditional relational databases, which are often less flexible when handling frequent changes in data structure. So, therefore, MongoDB was chosen due to its schema flexibility and document-based storage. And the main entities involved in our system are customers, orders, riders, and deliveries, which reflect real-world delivery operations. Next, I will explain our NoSQL data modeling approach. So our database uses the MongoDB document data model, where data is stored in collections and documents. So we design four main collections, which are customers, orders, riders, and deliveries. So each document represents one real-world entity. And we use embedded documents when data is closely related. So for example, the delivery status history is embedded in the deliveries collection. So this improves read performance and reduces query complexity. And arrays are also used to store multiple values such as order items and delivery status updates, allowing flexible tracking of delivery progress. And we also use reference, which are used to link collection. So for example, delivery references the orders and riders using object ID, which helps maintain data consistency without duplicating the data. And we also use the appropriate MongoDB data types such as number, boolean, date, object, and array to ensure data accuracy and clarity. And in a nutshell, our NoSQL data model balances performance, flexibility, and scalability, making it suitable for a real-world delivery record system.
Moving on to part B, I'm in charge of the CRUD implementation for our food delivery system. So we started with insert operations. First, we use the insert one method to register a new rider, which is Siti Aminah. And here you can see we use an embedded document for the vehicle field to keep the vehicle type and also the plate number together. And next, we use insert many method to populate our customers, orders, and also deliveries corrections simultaneously. And this demonstrates the efficiency of NoSQL in handling bulk data entry. So next, for query operations, we implemented several filters to retrieve meaningful data. We use the find one method for specific lookups like finding a rider by his name. And to filter data, we use comparison operators like equal operator to find customers the address that is in Skudai. Then we use a combination of greater than and also less than operators to find orders in a specific price range, which is between 15 to 20 ringgit. And also we demonstrate the logic operators like in operator, in operator to search for documents that matches any of the values in the provided list in a single field. Next, to find the riders that are available now or those who drive motorcycle, we use the OR operators to find it. And then the sixth one is we use the AND operator to identify the total amount that is greater than 15 and also the payment method, which is using e-wallet for payment. Finally, we perform array queries to search for specific items like teh tarik inside our embedded item list. And we also use the projections, which is using the include and also exclude to hide internal IDs while displaying only the customer names and also emails. So now we proceed to the update operations. So for the first one, update one method and also the set operator was used to update customer emails. And secondly, we are using the increase operator and also update many method to apply a 2 ringgit service tax to any order over 20 ringgit. Next, to manage our delivery timeline, we use push operator to add new status updates into the delivery status array, and we use the set operator to change our current status to out for delivery. And the last one, we use the pull operator to allow users to remove specific registered phone numbers from their profiles. So to conclude our CRUD summary, we demonstrated delete operations. So first of all, we use the delete one to handle order cancellations for specific transaction IDs. And we also applied delete many method with the not equal operator to offboard all riders who do not use motorcycle. So it is kind of to ensure our delivery standards are met.
Moving on to the advanced operation, we first implemented indexing to optimize our query performance. First, we create a single field index of the order date field. In a food delivery system, user and main frequently filter orders by date. For example, to see today's sales. This index allows MongoDB to find those records instantly without scanning the entire database. Secondly, we create a compound index using customer ID and total amount. This is critical for more complex queries, such as finding a specific customer's most expensive order. By indexing both fields together, we can jump directly to a user's high-value transaction efficiently. Next, we use aggregation pipelines to analyze our data. Our first pipeline calculates total revenue by payment method. We use the group stage to group all orders by their payment type, credit card, e-wallet, or cash. We then use sum to calculate the total revenue for each method. Finally, we added a sort stage to display the highest revenue method at the top. As you can see from the output, credit cards generated the most revenue, followed by e-wallets. For our second pipeline, we focus on the operational tracking. We want to measure rider performance, so we start with a mesh stage to filter only for orders with the status deliverer. Then we group the data by rider ID to count the number of completed jobs for each rider. We utilize project to clean up the output, showing only the rider ID and their total completed deliveries. This kind of queries is essential for calculating rider incentive or identifying top performance. We also demonstrated the sorting capabilities, which are vital for the user interface. We sorted orders by total amount from lowest to highest. This simulates a filter by lowest price feature for customers looking for budget meals. For descending sort, we sorted the customers by register debt in descending order. This allowed administrator to quickly see the most recently registered user at the top of their dashboard. Finally, I'd like to discuss the impact of index on query speed. Without index, if we search for order on a specific date, MongoDB will perform a collection scan. It's literally hard has to read every single document from start to finish to find the matches. This is slow and CPU intensive, especially as our data grows to millions of orders. And with our order date index, MongoDB performed an index scan instead. It used a B-tree structure to jump directly to the specific date like 2025 January 2 and skip everything else. This reduced the workload from scanning thousands of documents to just a few, making the response time almost instantly.
Alright, for my part, moving into the security, we must address that NoSQL systems are not immune to attacks. Unlike traditional SQL injections, MongoDB vulnerability often involve injective malicious BSON operator. For instance, an attacker might input a greater than comment into a password field. This makes the query return true regardless of the actual password, potentially granting unauthorized access to sensitive data. Beyond injections, we identify critical system-level vulnerability. First, weak default settings such as binding the database to 0.0.0.0 can exploit our customer log to the entire internet. Second, the segmentless design creates risk. Without strict validations, malformed input like massive string can trigger buffer overflow and system crashes, ultimately rise the data theft. Yeah, for this one, however, adopting NoSQL comes with trade-offs. We sacrifice strict ACID compliance for performance, which make multi-document transactions complex and resource-heavy. Additionally, the lack of service-side join forces us to handle relationship via application logic. This often leads to data redundancy, such as duplicating address, which increase storage costs and make updating shared data difficulty. In the conclusion, I will share that shifting to MongoDB significantly enhanced our development agility. We could learn to master performance through indexing and gain the crucial experience in data modeling, specifically balance embedded versus reference data. This project requires a major mindset shift to handle logic-based consistency and overcome constraints like only 16 MB document limit. For team contributions, Yuhin authored the introductions and lead the NoSQL data model design, identify our JSON structures and embedding strategies, while India was responsible for practical executions, documenting all CURD operations and capturing the necessary evidence from MongoDB Compass and Shell. Continuing with our team, Ziming implement the advanced technical operations, specifically handling indexing strategies and aggregation pipelining. Finally, me and I author the security and limitation sections, compile the final conclusions, and manage the overall formatting and editing of the report. This is for us. Thank you.